Every atom in your body was forged in a star. But life needed a world to bring those atoms together, to react, to copy, and to evolve. Tonight, follow the journey from star stuff to seawater to cells, and see how Earth became alive. Long before Earth, ancient stars fused hydrogen into helium, then into carbon, nitrogen, oxygen, and the metals that life relies on. When those stars died, they scattered these elements into a cloud of gas and dust. Under gravity, that cloud collapsed, ignited as our sun, and flattened into a spinning disk where dust grains collided, stuck, and grew. Within a few million years, planetesimals, mountain-sized worlds, merged into protoplanets. Impacts released enormous heat. One colossal collision with the Mars-sized body melted Earth's surface and threw debris into orbit, forming the moon. Heat didn't just destroy, it created structure. As early Earth remained molten, dense iron and nickel sank to form the core. Lighter silicates formed the mantle and a thin crust. In the liquid outer core, flowing metal plus Earth's rotation generated a magnetic field. That invisible shield deflected much of the charged solar wind, helping Earth keep its air and water. The young planet exhaled. Volcanoes released steam, carbon dioxide, nitrogen, and sulfur gases. Comets and water-rich asteroids delivered additional volatiles. Oxygen was absent. The early sky was thick with CO2 and water vapor. But as impacts waned, Earth radiated heat to space, surfaces cooled, and water vapor condensed into clouds. Then the rain fell, likely for thousands of years, pulling into the first long-lived oceans. Even though the young sun shone fainter than today, greenhouse gases kept Earth warm enough for liquid water. Oceans formed a universal solvent, dissolving and transporting minerals and molecules across basins, shorelines, and hydrothermal systems. On mineral surfaces like clays and iron-sulfur compounds, reactions could concentrate and organize molecules. Along shorelines, wet-dry cycles help link small molecules into longer chains. In the deep, alkaline hydrothermal vents offered natural chemical gradients, energy batteries, across porous mineral walls. Lightning, UV light, geothermal heat, and chemical disequilibrium powered countless microscopic experiments. Life doesn't require a perfect lab, just many good chances. Earth offered oceans, energy, catalysts, and time. With the stage set, the question became, which pathway turned simple chemistry into the first system that could copy itself? Scientists explore several complementary pathways for life's origin. One promising setting lies at alkaline hydrothermal vents. There, warm, mineral-rich fluids seep through porous chimneys into colder ocean water. The tiny pores act like natural compartments, and the chemical gradients across those walls can drive reactions that build organic molecules. Iron-sulfur minerals may have helped spark primitive metabolism, simple networks of reactions that capture energy and build complexity. Another pathway is the primordial soup near the surface. In shallow pools and along tidal flats, cycles of wetting and drying could concentrate building blocks. Energy from sunlight and storms can help form amino acids, nucleotides, and other organics. While no single environment is perfect, the combination of concentration, energy, and cycles can push chemistry forward step by step. The RNA world concept offers a unifying bridge from chemistry to heredity. RNA is special. It can carry information like DNA, but also act like a catalyst, speeding up reactions. If early chemistry produced sure RNA-like molecules, natural selection could favor those better at copying themselves or assisting useful reactions. Over time, systems that stored information more reliably, DNA, and performed tasks more efficiently, proteins, could take over, leaving RNA to key roles like translation. Compartmentalization is crucial. Fatty acids can self-assemble into vesicles, tiny bubbles that trap molecules inside. These protocells concentrate ingredients and protect fragile polymers. If some vesicles grow, divide, and pass on helpful molecules, they can compete and evolve. Even small advantages, faster copying, better energy capture, would be selected for in a world of countless trials. These pathways are not rivals as much as partners. Shorelines might favor polymer growth. Vents might favor energy capture and metabolic cycles. Meteorites and dust could supply rare ingredients. Through mixing and time, different steps could converge. Compartments that house replicators powered by simple metabolisms. When copying with variation and selection emerges, chemistry crosses into biology. The exact first pathway remains uncertain, but the direction is clear. From simple molecules to self-sustaining networks, from networks to replicators in compartments, and from that to the earliest cells capable of evolution. Once replication and selection began, evolution took over. Early life almost certainly lived without oxygen, drawing energy from chemical gradients around vents, minerals, and dissolved compounds. Chemoautotrophs could fix carbon using energy from reactions with hydrogen, iron, or sulfur. Others fermented organic molecules made by their neighbors or by geochemical processes. A revolutionary innovation arrived with photosynthesis. The earliest versions didn't produce oxygen. Later, cyanobacteria learned to split water, releasing oxygen as a byproduct. For a long time, that oxygen reacted with dissolved iron, settling to the seafloor as banded iron formations. Eventually, sinks filled and oxygen began accumulating in the atmosphere. The Great Oxygenation Event transformed Earth. Oxygen enabled new, more efficient ways to harvest energy and altered climate and chemistry. Some lineages suffered or retreated to anoxic niches. Others adapted, setting the stage for more complex life. Inside cells, another breakthrough reshaped biology: endosymbiosis. Ancestral cells formed partnerships with bacteria that became internal powerhouses, mitochondria. In plants and algae, a later partnership produced chloroplasts. With mitochondria boosting energy budgets, cells evolved more complex structures and processes, unlocking the potential for larger genomes and new behaviors. Multicellularity evolved multiple times. Simple clusters coordinated, then specialized. Tissues and organs emerged, ecosystems expanded, and life began to shape the planet as much as the planet shaped life. Photosynthesis pulled carbon from the air. Weathering and burial locked it away. Oxygen rose. Climates oscillated. Diversity blossomed and crashed and blossomed again. The big picture is astonishing. Elements from dead stars fell into a disk, accreted into a world, and organized into oceans, rocks, and air. Energy flowed through minerals and molecules until some reactions learned to copy. Copying allowed selection. Selection built complexity. Complexity built cooperation. Cooperation built ecosystems, and eventually a biosphere that transformed Earth. The creation of life on Earth isn't a single spark, but a chain of opportunities. Ingredients, energy, cycles, compartments, copying, and time. Each step made the next more likely, until life became not just possible, but inevitable on a world like ours. From star-forged atoms to living oceans, Earth shows how physics and chemistry can become biology. If these steps happened here, could they happen elsewhere? In future episodes, we'll explore icy moons, ancient Mars, and distant exoplanets for signs of similar pathways. If this journey sparked a curiosity, subscribe to Mantle and Mythos, explore the Origins playlist, and tell which step you want to see visualized next.